Okay, in the second part, we need to talk about the important properties and theorems of Z transform. Okay, so in the first place, you need to say that if we have the any function just like this one with the multiplication with the a, we can evaluate this signal a times z x t. Okay, it's the multiplication property. It's simple. In the second place, we need to talk about the linearity. For example, if we have the x k is equal to alpha f k plus beta g k, and then we can represent the z transform just like this one. Z. Okay, this is the linearity proposition of these terms. Otherwise, we cannot apply the z transform in here because it must be linear. Okay. Thirdly, we have the shifting property. For example, z x t minus n t, just like this one. We can evaluate this signal based on the what? Z t is a constant value minus n x z. Okay, this is a simple property. Or if we have the z x t plus n t, just like this one, z n times x z, but with basic difference, k equals 0, n minus 1, x k t times z minus k. Okay, this is the simple property of the what? The z transform. If we have the reverse operation, the backward operation, we can just use this implementation. But if we going to forward in this direction, and then we have the xz value in here with the multiplication of the zn, this is a positive value because we have the positive value in here. But otherwise, we have the n minus 1, which is the what? For example, n is equal to the 4, and then we can write that the x1, x2, x3, and x4, right? If we have the zn, and then we should write or remove or subtract the what? The 3, 2, 1, 0. In this case, because it's a forward process, we can easily take the backward because it happens in time. But if we going to forward, and so we should remove the whole the terms before the what? The 4 or 5 or 10. Okay, this simple shifting rule for the what? For the z domain. Okay, and so if this is the case, we should write the 3 shifting is continue in here, just like this one, using this theorem. And so z, for example, x k plus 1 is equal to the what? Z x z minus z x 0. This is the initial value theorem, right? If we have the initial condition just like this one, because we have the n, for example, k plus 1 or k plus 2 can be written also in here, just like this one, k plus 2, right? And so we have the z square xz minus z square x0, because we should move this value to the what? To the 4, 2. I'm sorry, 2. Or we should subtract this value from this one, and we should also subtract the z x1 value in here. Okay, this is the initial condition of the Laplace transform, but in Z domain we can utilize this theorem based on these informations. Okay, just remember that in the Laplace transform, if we have the initial condition, and then we should apply this transformation just like this one. Okay, the important note is that we don't have any derivative or integral operation in discrete time domain, because we have the forward value and the backward value in here, just like this one, nothing more. Okay, and so another property is that we have the final value theorem. Just like in the S domain, we have the condition of this, that limit t going to infinity value ft can be represented in the time domain as the limit as going to 0 s times fs, right? This is the continuous time theorem. Okay, and so consider this example in here, just like this one. Consider tf like hs is equal to 1 s plus 1, okay, and apply it on unit step this transfer function, which is equal to the 1s. This is the unit step transfer function in here, and so the output yt, or in another terms the ys, can be described with s plus 1 times 1s and s plus 1, right? This is the output values of these terms. And so in order to find out the final value, t must be going to infinity value for the yt, but in Laplace domain we have the s going to 0. It's the inverse values of the time. Okay, and so s times ys should be multiplied, and also limit s going to 0 value s plus 1, which is equals to the limit s going to 0 1 s plus 1, which is equal to the to the 1, right? Because this s represent the 0, and so 1 divided by 1, it's equal to the 1. And so how can we implement this information in the Z transform? If we have this condition, and then in Z transform we have the limit k going to infinity value for the xk, right? K is the sequence, xk is our values, instant value at each time. Okay, and so the limit z is is not taken the 0 value, is the 1 value, because the steady state value in this domain is represented with the with this nomination. Okay, the z is equal to the 1. I will explain why in here. And so this transform is represented the -1 z times x z. Okay, these are the basic notion coming from the our theorem. Okay, and so why do we need to do that? Just remember the unit step impulse response, unit step response in here. 1 divided by 1 minus z over -1, right? And so this is just kind of the s in the Laplace transform, but in Z transform we have this information, this property. Okay, and so we have an example in here, just like this one. Determine the final value of, for example, xz, which is equal to the 1 divided by z1 times, this is the unit step, this is the output response of our system. Okay, and so the system can be given y minus e a t times z minus 1. This is the z transform of the what? The exponential over a times t. Okay? This is our sample system. Okay? And so, how can we analyze this function in terms of the what? The final value theorem. And so, x infinity value is equals to what? The limit z equals to the 1 minus z1 times xz, right? And so limit z going to 1 minus z over minus 1 z over 1 minus EAT z over minus 1. Okay, these are the theorem. Okay, and so this is equals to what? The 1. This equals to EAT in time domain. Just remember that. Okay, and so this is simplified as the z going to 1 value in here. This is 1, right? Because these terms cancel each other, and then we have minus z over minus 1 minus exponential a t times z over minus 1, and so this 1 terms removes each other, and this is going to what? Equals to the 1. Okay, if you put the 1 value in here just like this one, this is 1, and so this cancels and we have the 1 value in here. Okay, and so why do we need to use the 1 in this case? I can explain it. Just remember that in S domain and also Z domain in here, just like this one. If we have the S domain in here, sigma and JW, what's the stable range for this domain? Yeah, no. So, how come we stabilize the system selecting by the roots on this S domain? We have a region in here, just like this one. If our poles at the left hand side of the S domain, just like this one, and so we can call it a stable. Because Hüsamettin, because for example, if we have the minus 2 and minus 5 in here, just like this one, this yields to the what? To this kind of response, natural response. Okay? But if we have the roots at the right hand side of this S domain, and so this generates to what? The positive value in here, and it's always growing in time. Okay? But in the Z domain, we have different values, different notion. For example, if we have the n equation just like this one, k plus 1 is equal to the what? The 0.9 times xk. For example, the x0 is equal to the 1. What is the outcome of this signal? If we increasing the k value, this is the first value. What happens if I run this diagram? This equation is run, and then we will have, for example, at the 1, 2, 3, 4, blah blah blah. This is the first value. In the second, yes, and so in the 2, yes, and so we have always decaying values, decreasing all the time. For example, if we have the k plus 1 is equal to 1.1 xk, and so how about the time response or the sequence response of these terms? In time, we have 1, 1.1, 1.2, and so we goes to infinity, right? Okay, what happens if I choose the k plus 1 is equal to 1 xk? Stable, right? And so we have the 1 value in here, just like this one. And so this represents to the what if we have using to what the bigger than 1, we have unstable region. Smaller than stable region. Okay. And so we have a line at each case in here. And so I can draw these values, sigma and j omega value in here, just like this one. And so we have a unit circle, I think, in here, right? And so the maximum value of this term must be equal to the 1, okay? And so in this z domain, if we have any pole, any line smaller than 1, and so we have stable region. Okay, in summary, and also I should take this one, k plus 1 is equal to minus 0a9 and xk. This is stable or not? Just drawing the signal xk, first 1, 0, minus 0.9. This is stable or not?
Stable, but it has a lot of fluctuations.
Yes. And so in here 0.9, and so just like this one, right? And so if we have the minus term in here, and so we have stable part, but oscillation happens in here. Just see that. Just remember my first Euler identity depiction. I can always only drawing to what? This kind of implementation in here. Why? Why? I use only the what? The right hand side of this function. Why? Yes, oscillation is also happening here, but we can take the region in here with the values of the absolute, okay? And so either the negative or positive value can be stable if this value is smaller than 1, okay? And so our function or the stable region at the z domain can be described with the what? With this nomination 1, minus 1, 1, minus 1, right? And so we have the stable region in here, just like this one. And so in the z we have the r, e, j, theta, right? This is the z, and so this r must be smaller than 1, and so we can say that this system is stable, right? This is the r. Smaller than z is equal 1, okay? But if this is equals to the 1, and so we don't have any change from this pole, right? Yes. Yes. If we have this kind of system, for example, xz 1, z minus 1, and z minus 0.5. This is the pulse transfer function. What's the condition of these terms? It's stable or not? Stable. Why? Yes, 1 and 0.5, right? Okay. Z plus 0.9, z minus 1.1. Stable or not?
Not stable.
Not stable. Why?
Because our poles we have one is bigger than one.
Yes. Stable or not? Stable or not?
Is it 0.6 or 3.6?
0.5, 0.6.
Okay, stable.
Stable. But with this is stable, but it has also oscillation. right? This is simple implementation for the what, for the condition of the R system in the Z transform, and so it does not affect it from the what, from the sampling period in this case. If you are using the different sampling period in here, just like this one, and then we can say that this system is stable if the magnitude or the hypotenuse of the Pythagorean triangle smaller than 1, because at each case we have this signal just like this one. Just remember that this is the Z x Z minus 9 x Z, right? This is the basic representation of these terms. And so if we take this value, x z is equal to what? The z plus 0.9 is 0. And so we have the R response of this system. Okay? We can check it easily just using this theorem. Okay? So the last topic about this lesson is the what, or the last property, poles and zeros, right? In this pulse function, xz can be represented by with the what, with these coefficients. b0 zm plus b1 is a coefficient of this term, z minus 1 plus blah blah blah, and bm z0, right? This is the general representation of the zeros in here. Or we have the denominator part, zn plus a1 zn minus 1 plus blah blah blah, and an times z0. Okay, this is the general definition of the what, the pulse transfer function. Okay, this kind of the transfer function in the Laplace domain, but we have the basic difference, which means that if we are using the z or the polar coordinate or the line in Euler identity, we can write it down, and so we can split each range to the what, to the sampling periods. But in Laplace transform we cannot do that. Or we can simplify this notion as the what, the x as z is equals to the what, the b0 times z minus 1 z minus 2 blah blah blah, and z minus zm, right? Why is this equals to the m? Zm. Why? We have, yes, we have m order value in here, and so this equals to what? Pn. Why? It's the n order equation in the denominator. Okay, and so pi is the poles and zi is the zeros, and so the poles are important for the what, for checking the stability of this system. Okay, it's kind of the characteristic equation in Laplace transformation. Okay, and zeros is always affect to what, to output results, the transient especially results, but it does not affect to what, to main characteristics of this system. Okay, and so we can analyze the discrete function based on these informations. Okay, any question? Okay.